there was a little bit of confusion that I had that I'd like to clarify. So I want to sort of go back to the beginning and review a few things. So what we're interested in is deriving the equation of motion that describes the evolution of a quantum system in an open quantum system context. Okay? And so to do that, we appeal to what we know about and what we learned about in basic quantum mechanics in thinking about deriving the equations of motion for quantum systems in the closed quantum system context, right? So if I have a closed quantum system, then we know that the sort of input-output map for a closed quantum system is a unitary operator. And so the unitary operator takes us from the input t to the output time t2. And the state evolves according to that unitary map. In order to get at the equations of motion, we need to think about the so-called generators of the evolution, the near unity unitary maps in a differential sense. And the generator of dynamics is the Hamiltonian. So the Hamiltonian is the generator of time translations. So what that tells us, I could write a unitary map that takes me from some time t to some differential time, some short time dt later, that is something that is close to the unit operator with a small differential addition that's proportional to the Hamiltonian. Okay? And from that, we can derive the differential equations. For example, we can derive the Schrödinger equation. So the Schrödinger equation, written as an equation of motion for the state of the system, just tells us how to differentially map from time t to time t plus dt. And keeping those terms to order dt, that has the following form. Okay? It's the density operator time t plus dt is what it is at time t with a little piece that's proportional to dt. And that little piece there is the proportional to the commutator of the Hamiltonian with rho, or I could write it in a fancy way for a reason that maybe will make be clear in a moment. I can think about this in terms of the Lie bracket, the add of this operator with this is just another name for the commutator. Okay? We could also look at this as a differential evolution for what the unitary map is itself, right? And this is another way of sort of we sometimes call this thing the Schrödinger equation as well. It's the evolution of the unitary operator. And there is a general solution to that, which is the time-ordered exponential with the argument being the integral of the Hamiltonian. And in the particular case that the Hamiltonian, for example, is time independent, then this has the standard form that we're familiar with, right? Okay, so now the goal here is to take these things and translate them into the open quantum systems context. So we know, first of all, we discussed the general input-output map is a CP map, okay? And contrary to what I was saying in a garbage way last time, yes, this is a function only of the initial time and the out and the final time. That's the map. And so the state at some time t2 greater than t1 is whatever this map is acting on the state of t, time t1. Okay? So now what we're looking at for is what's the generator of the dynamics. And this is where the story comes in. So we conjecture a particular form for the near unity map that is generated by something we call the Lindbladian. Okay. This Lindblad is itself a superoperator. It's a map on density operators. And we conjecture the following form. A form that is analogous to this form. Okay? Or I should say analogous to this form. Which is to say that the differential map that takes me from time t to dt, t plus dt acting on the state, is the state plus something that is local at that time times dt. Okay? And that this thing only depends on t and not dt. Okay. So that is the Markov approximation, or the Markov form. I never know whether Markov is with a V or two F's. It's written both ways, and I seem to go random on it. But I'm going to stick with V.
I think it depends on your conventions if you convert it from Cyrillic.
Yeah, I don't know. It seems to be written in both ways in the literature, and I tend to do that too. Okay, so this, as we will see, as we will in a moment, is only ever approximately true. Okay. But if we conjecture this form, then we end up with a local differential equation for the density operator. What it says is, if I just look at this, what the state is at time t plus dt, it's equal to the state of t plus this bit times dt, subtract off, and you get this differential equation. This is the master equation. Okay. And in principle, this too could be integrated, and we sometimes do that. So the map itself is generated by the Lindbladian. So if I wrote this as a superoperator, say this was a d-dimensional Hilbert space, then this thing would be written as the density matrix itself is a d by d matrix. The Lindbladian is a d squared by d squared dimensional supermatrix, where I can imagine vectorizing the density operator as a column vector with d squared elements, and then this is a d squared by d squared matrix, and I can exponentiate that, and that would be the superoperator map. And that's what we do all the time if I'm trying to simulate these things. Okay, it's one of the ways we could do it. And generally, I mean, it's typically the case that the Lindbladian will be time independent unless the Hamiltonian is time dependent, because you have some control fields that are classical control fields that are functions of time. But typically, you time independent and just exponentiate it. Okay? Now, this is a generic form. What we showed furthermore in the lecture last time was that just from the fact that this is a CP map, it has a Krauss representation. And based on that Krauss representation and the fact that we look for trace preserving that the Lindbladian was the following. It was equal to, in principle, the minus I commutator H effective as a function of time, or right this way, H effective rho minus rho H effective dagger plus sum over mu L mu dagger. All of these can be functions of time, so let me just put that in. where, or where H effective is a non-Hermitian operator whose Hermitian part is the Hamiltonian and whose anti-Hermitian part is given by this sum. Oh, sorry. This sum. Principal, everything could be a function of time if I'd like it to be. And this set, so often you will see this written as minus I over H bar. So LT rho H comma rho plus sum over mu minus a half mu dagger mu rho. I'm going to leave out all the explicit time there, but just remember that in principle everything can be functions of time plus mu rho mu dagger. So this is known as the Lindblad form.
And there should be an I in the definition of H effective, right?
Indeed. Sorry. Minus I H bar. Indeed. So this is the Lindblad form of the master equation. This is the time derivative of rho. And these operators, L, are called the Lindblad operators. They're also called the jump operators. Let me try to explain why. I should say, to re-emphasize, the Lindblad form of the master equation doesn't have to necessarily be trace preserving, but if I want to say, in this case, as I've written it, as a trace preserving evolution, an evolution that you can check for yourself. If you take the trace of both sides of this equation, you'll get 0. Okay? Try that, it's easy. This is the unique form of the equation which is Markov that generates a CP map. Okay. All right. So what about these Lindblad operators? How do I interpret what they mean? What is the sort of physical meaning of the Lindblad operator? We know what Hamiltonian is. What about the Lindblad operators? Well, in some sense, they have to do with the irreversible part of the evolution. This part, if we didn't have this, this would be the Schrödinger equation, and that would generate unitary evolution, and that is time reversible. This part is sometimes called LDK. So that's the decay part, the part that has to do with the irreversible evolution of this system. Let's just look at that part. Let's forget about the Hamiltonian for a moment. And let's just look at what the effect is of this evolution on the density operator. We've studied this. We studied this last semester where we wrote this equation just phenomenologically, right? Yeah.
Is there a dagger missing from the message?
There is. There's a dagger missing. Sorry, thank you. Indeed, there was. Right. Okay. So let's look at the following situation. Suppose. So let's consider the evolution of the diagonal elements of rho in some basis.
for the notation, LDK includes the
Everything.
everything.
Everything that's not the Hamiltonian. Sorry, yeah, indeed, everything. I mean, really, I think a better word for that would, because it is a little bit confusing, let me call it the dissipation. Because there is a little subtlety there. That is kind of, we'll get to it, which we studied a little bit last semester. So let's say we are in a situation where, let's just for the moment assume that the density matrix is diagonal in some basis. Let's say there are no coherences. We can come back and put the off-diagonal matrix elements in, but let's just say that the density matrix is such that it starts off with no off-diagonal elements, and we want to know how do these populations evolve as a function of time. Those populations are the diagonal matrix elements. Okay? So let's take a look at that. So we could just plug that in. We'll take the Hamiltonian to be 0. Okay, we can do that. We're in some picture where there's no dynamics that we care about. It's all the dynamics due to this dissipative term. And let's look at what that does to these things. Well, so the time rate of change of those populations is equal to the time rate of change of the density operator matrix elements. And then we just plug that in. So what am I going to get? What I'm going to get is the following. Let's just, for clarity, let me call this K, just because I use J as my dummy index, so I don't get too confused. Okay? I'm summing this over J as a dummy index. So that is going to be equal to when I hit this on this side with rho, I'm going to get a delta j k. It's going to pick off the kth element here. So I'm going to get minus a half sum over mu k L mu dagger L mu k pk plus, now I hit it from this side, again, it's diagonal, so I get k L mu dagger L mu k pk. Get two of those terms, they're the same. And then I get plus sum over mu sum over j k L mu j L mu dagger k p j. Okay. You buy it? Right. So this has a simple form, a form we're familiar with. This is the form of a rate equation. It says the population, you know, like the foxes and the rabbits, change in some rate equation way. Population in level k is decaying with some rate omega k, gamma k. Then I have a plus sum over j, something I'm going to call gamma from j into k pj, where my gamma sub k is equal to the expectation value in the state k of the sum over mu LU dagger mu k, and the transition rates from k into j, or from j to k, the way I've written it, is equal to the sum over mu, the absolute value of the matrix element of the Lindblad operator between those two states squared. So, what that tells me then is the following. These, if I look at that equation, it says the population in level K is decaying out of level K with this rate, and that population is being increased in level K depending on transitions from levels J into K, weighted by the probability that I started in J.
There's also J is equal to K in that.
There is. Indeed, there is. So we could, if you, so that's a good point. That includes all possible, includes the J equals K term. But before I get to that, let me just make one statement. This relates to the point that you noticed earlier. Obviously, this is the total decay out of level K. And these are the refeeding from J into K. This was a jargon that we used last semester when we were looking at the spontaneous emission of atoms, where we noticed that the imaginary part of the effective Hamiltonian, the stuff that I just erased for some stupid reason, was the stuff that had to do with the decay of that level. And then this term, or sets of terms, represent the refeeding of the population back into a particular level. The decay part looks like Hamiltonian evolution, but with an imaginary energy. Whereas these terms don't at all look like Hamiltonian evolution at all. And where that's going to become important when we look at the problem of quantum trajectories in a few weeks. But just to emphasize one more point, and that was related to a point that Amir noticed. If I like, I can insert here a sum over J, a complete set of states, right? In which case this is equal to a sum over mu K, or J, L mu K squared, which is equal to, I have a sum over J. A sum over J from K into J. As we expect, the total rate of decay of level K depends on the sum of all the partial rates to all possible J's. Now, of course, when I plug that into here, the part where J equals K cancels. So I can also rewrite this as minus, now J not equal to K. I could keep this total sum there, but it's not relevant because those terms cancel. So that's the general form that you might expect of rate equations between different levels. The total rate of change of the population in level K, there's a decay out of K into every possible J, not back into the same, with a particular transition rate from K to J. And there is refeeding of population back into K from all other levels J, weighted by the rates. And here's the key point to remember, how you should interpret the Lindblad operators. The matrix elements of the Lindblad operators tells me the rate at which transition happened from level J into level K. That's why they're called the jump operators, because I can think about this as if I had a bunch of energy levels, the rate at which dissipation causes a jump, a quantum jump if you like, from one level to another is determined by the matrix elements of the Lindblad operator. Okay, that's interpretation. Yep.
Just here where you've excluded things, you've just taken two terms.
That's right. The term where K and J are equal cancel each other, and that's what you're left with. So, given that, I mean, we could, without going through the very difficult physics calculation that I'm about to do, hopefully in the last hour and a half of the class, we could write down what are the Lindblad operators say for the case of a two-level atom interacting with a vacuum. We could guess them. So let's consider the problem which we're going to solve by first principles and Wigner-Weisskopf and all kinds of challenging Markovian gymnastics. What is the Lindblad? What are the jump operators? Or what's the, for an atom, which is the system, interacting with the vacuum, which is the environment. Well, what do we know? What is the transition rate from there? That's my two-level atom. There's only I have dimension 2. So J here, the set of states J are the ground state and the excited state. Okay. So, what is the transition rate from, say, the ground state to the excited state if I have the atom in the vacuum?
0.
0. Can't forget, if it's in the vacuum, this is 0. And what's the transition rate from the excited state to the ground state? Let's start the atom in the excited state, it's in the vacuum, or actually I don't necessarily start in the excited state. The atom is in some arbitrary state. Well, no, in this case it is. It starts in the excited state. So what is that rate?
Einstein.
Yeah, it's the Einstein coefficient. So, right, that was 4/3 the dipole matrix element squared over h bar times omega over c cubed. Omega is the frequency of the transition. So what are the Lindblad operators then? The Lindblad operators have to be such that you take the matrix element between those things, you get those rates. Anyone have a guess? it's got to be the lowering operator, right? So L, it's got to be proportional to sigma, right? That's the operator that takes me from, but it's not quite enough, because where's the Einstein A coefficient in there?
Which is multiplied, right?
Times the root of gamma. Right? Such that if I look at the matrix element of this squared, I get gamma. So we could write down the master equation for our two-level atom. It's equal to whatever the Hamiltonian is. Plus, there's only one Lindblad operator here. So we have minus gamma over 2, sigma plus sigma minus, rho plus rho, sigma plus sigma minus, plus gamma sigma minus rho sigma plus. And if you look back somewhere, I'm sure in some lecture that we have, that you read so carefully and remember every detail, this was the master equation we wrote down last semester. It is of that form, with this as the jump operator. And in fact, if I plug this in, this is sigma plus is the raising operator. This is EE rho plus rho EE. This is plus gamma G G rho EE. Which of course is equivalent to having the Hermitian Hamiltonian, non-Hermitian Hamiltonian, where H effective is equal to the Hamiltonian minus I H bar gamma over 2, L dagger L is EE. Right? This is L dagger L. Which represents the decay out of level E. And this represents so this is the decay, which is given by the imaginary part. So remember, our two-level atom, it has a line width by the time energy uncertainty principle. The fact that it has a finite lifetime gives it an imaginary part of its eigenvalue. And then there's a refeeding term which says if there is a spontaneous emission, then the atom must jump from the excited state to the ground state, and the probability of that happening depends on what the population is in the excited state with a rate gamma.
And what dictates the fact that there is only one jump operator? This is the physical process of...
Well, as we discussed, this is not unique. So I can, and we can do a unitary remixing of this and write down an uncountably infinite number of different master equations which generate exactly the same evolution. This is one possible such Krauss decomposition, but it's not the unique one. Okay, so that's cool. If you really want to grab an early dinner, you can do it now, but we're going to now rederive this, and we should stick around, from, really we guessed it, but it should come out of the physics. So that's what we want to do. What we want to derive this from first principles and show where the rabbit goes in the hat when we make the Markov approximation, because we can only get this form approximately, and then how we ultimately get, for the specific example of an atom with the field, this kind of master equation. So that's where we're headed. All right, well, that
Actually, I've got a question.
Yes, please.
So I guess it seems like, I mean, the method that we just used is basically analyze what's going on physically, you know, determine some rates, and then use that to set the matrix elements
Yeah.
of your Lindblad operators.
Yeah.
But it seems like that scheme, if you use that, that would always give you a single jump operator.
Not necessarily. It depends on what all the rates are. Here's an example. Suppose I have an atom with substructure, okay? So let's say this is this S1 half ground state and a P1 half excited state as two magnetic sublevels. If this atom here, there's two possible jumps. It could jump like that and it could jump like that. So there's a total rate of decay, but the refeeding will depend on the
Okay.
polarization of light in this case. So in this case, you have multiple jump operators.
But again, it's just it's just a convenient way to represent that process. It's not that you cannot write any, a different number.
It's true, but I'm not sure it's the case that I can always reduce it to one.
Yeah, okay.
Okay? I think I can always make more, but I don't think I can always make one.
Yeah.
Okay? So it will depend in this case, and we could write these down. I need to know the Clebsch-Gordon coefficients, and then I can figure out what the branching ratios are for these different processes, and I write down different jump operators. And they're, due to the fact that there's more information in the environment than just the energy of the photon, there's the polarization.
Okay.
Now, yeah, we'll come to that. There's going to be some more
Yeah.
cool stuff about it. All right, great. Excellent. So let's continue then. So remember, what we want to do now, we want to derive the Maxwell equation. From first principle system environment interaction. So the picture that we have here is one in which we have the environment, we have the system, we have some Hamiltonian, which is some Hamiltonians that act individually on the system and the environment, and some interaction. Okay? And in the interaction picture, the total state of the joint system environment evolve according to the Schrödinger equation, bless you, where the interaction is the generator of the evolutions, where the interaction Hamiltonian is has the system environment degrees of freedom evolving according to the free Hamiltonians of system and environment. All right, so from this, we can try to derive our near unity map. Okay, we just integrate this. For a short interval dt, ultimately try to look at the differential and what that means. So that's equal to that plus the sum from, where minus I over h bar from t to t plus dt, integral over times dt prime of that. Okay. And so if I'm interested in particular in what the evolution is of the system itself, I need to trace out the environment. So that's the system at time t minus I over h bar integral t to t plus dt, dt prime, the trace over the environment, h system environment, dt prime, rho system environment. So now there's a problem, because this is not of this form. This integral depends on the whole evolution between t and t plus dt, and not just on t alone, but everything within that history. And that's, as we said, is because their information can go from the system into the environment, but then back from the environment into the system. That's the actual complete description of the coupled system. And in principle, that can happen. So this is not in the Markov form. In order to get the Markov form, we need to do an approximation and justify that approximation. All right, so let's see. Remind myself where I want, what I want to do next. Right. Yeah, I guess I could say that this is generically of the form of some let's see. This you might call the memory kernel. In other words, there is some way, if I can express this, it's an integral differential equation that depends on the whole history of what happens throughout the interval, not just what it is at time t. It's only when there is no memory that I can throw that out that I can make this in the Markov form.
You didn't add this term, right?
I'm sorry. I'm saying this could be, what I'm saying is this is approximately, I'm saying not plus that, pardon me. I'm saying this could be approximated through this way. This is the more generic form. But the Markov form is an approximate form where this is essentially a delta function.
You're not saying that this could be written that if you choose the right memory kernel, that is exactly.
Yes, no, that is what I'm saying.
That's exactly
Yeah.
that for the correct memory.
For the correct memory kernel. It's an integral differential equation, always. There is an exact integral differential equation for the state of the system once I trace over the environment, but it's not exactly a differential equation. Now, what that is a complicated thing, and I don't even know how to do it. But if we have the Markov approximation, then what we're going to see is that this is you know, of the form that we want, it's some Lindbladian delta t.
In the general case,
Mhm.
is the memory kernel an operator? Or is that?
That's a good question. Is it a map? Yeah, that's probably the most generic way to say it, that this is some CP map like that. I think that's correct. It wouldn't necessarily just be a scalar. Let's see. Yeah.
So in that case, the density operator has to be a function of the Hamiltonian?
I don't know what you mean by that. The density operator evolves in a way as a function of time that depends on the Hamiltonian. So in that sense, the time evolution is a function of what the Hamiltonian is. Right? But this kernel, I've traced over the environment and I've left with effectively some map on the system. It's just not one that's Markov in this form. All right, let's look at the particular case though, where we can, that's what we're really most interested in, the case that's most relevant in, particularly in quantum optics, where the Markov approximation is excellent. It is true that in many dissipative focal quantum systems, and particularly in condensed matter, the Markov approximation is not good. And we'll explain why that's the case. And generally, much harder to deal with exact models by master equations in treating dissipation in condensed matter systems. It's a real pain. But in quantum optics, it's awesome. And so we can be Markov and be happy. Yeah.
I mean, this is a little bit tangential, but it seems like in most cases in which you don't have some sort of like, I don't know, preset time scale that basically have kind of time invariant dynamics, and you have a situation like that, you can Fourier transform, and then basically, you know, your kernel just becomes a multiplication in the Fourier domain.
Correct.
Is that, I mean, is that something you can do here? I mean, look at the density operator as a function of...
Absolutely you
Okay.
can. So what, as we're going to see, and that's maybe another thing to say, is the spectrum of something related to the interaction is a indicator of what the memory kernel is. So if the spectrum is essentially white, then the memory is essentially delta. That's the Markov approximation. So people talk about white noise versus colored noise. If you have colored noise, then you have memory kernel. If you have white noise, which the vacuum is, then you have essentially delta correlation.
Okay.
So let's look at that more specifically. Right. Okay. So as we said, in order to deal with this problem, the fact that there is a finite memory time, we're going to coarse grain. So the idea here is to take delta t to be much greater than whatever the correlation time is of that memory curve. And ignore any dynamics that happen on a time scale that's related to where information can go into the environment and come back. this will be a useful approximation, a useful coarse graining, if and only if, at the same time, delta t is tiny compared to whatever the dissipative dynamics of the system. So the analogy I gave in the last lecture was just one that is, it's essentially the same thing. If you drop the penny in the lake, and the lake is at temperature T, the penny is way hotter than that, there's a time scale associated with the correlation of the collisions of the water molecules with the hot penny. But then there's a time scale over which it quickly rethermalizes. And those molecules that got out of equilibrium quickly rethermalize. That time scale is what I'm calling tau c. There's another time scale, which is the time scale at which this thing comes into equilibrium with tau. But that's a way longer time scale. And so when there is this kind of separation, then we can effectively coarse grain treat this time scale delta t as effectively differential time with respect to the dynamics, the non-equilibrium dynamics of the hot penny, although it's infinite time compared to the rethermalization of the environment. That's the whole story of how we end up going from something which is in principle reversible dynamics and getting something which is effectively and an awesome approximation irreversible dynamics.
Just to be clear for something you said at the end of last time, nothing about that is inherently quantum mechanical,
isn't.
correct? That's
No.
just,
Yeah. So the same thing is true in classical non-equilibrium open classical system dynamics. Indeed, that part of it.
right.
This separation of scales. What is going to be quantum, as we'll see, is that we could, as the problem that we just looked at earlier in this lecture, where our bath is not water, but the vacuum, then it's at 0 temperature, right? But it still has quantum fluctuation, quantum noise. But you can think about that as, here's my atom. Atoms look like this. But there's little wave packets of the vacuum that are flying by this guy. The time it takes to transit the atom is an attosecond. I don't know, something like that. Tiny, tiny amount of time. But that's nothing compared to the time it takes at least nanoseconds for the atom to decay. So the correlation time of the vacuum with the atom is effectively 0 time compared to the time it takes the atom to decay. Now, in this case, that is not a classical collision. It's going to be a quantum entanglement between the modes of the field and the atom itself. Excellent. All right. So, let's see. All right, so we want to solve this problem. To do this, what we're going to do is, essentially what we're looking at is the master equation version of Wigner-Weisskopf that we studied last semester. And effectively, we're going to derive, again, the spontaneous decay of the atom, and that will require us to go to at least second-order perturbation theory. That's how you get time-dependent perturbation theory using decay. So I'm going to iterate this equation here to the. Right now, this is an equation, say written in this form over here. This is self-referential. It's not actually a solution. So we need to iterate this to some order and then truncate. So we're going to go to second order here. So I'm going to plug back this solution into here, and I get the following. So to, let me just write that out. So I plug this back in, I get that, so this becomes a t, and then I get plus minus I over h bar squared, the integral t to t plus delta t dt prime from t to t prime dt double prime h in double prime. So that's giving me ultimately the Dyson series. Yeah.
H infinite is the same as H SE.
Oh, gosh, yes, I did mess up my notation there. Pardon me. Let's keep it straight. It's the interaction between, yes, pardon me. Two forms of my notes, I have two different things. And now what I'm going to do is just truncate this, so this is 2-second order. In the interaction. So as long as my delta t is short enough, I can do perturbation theory. The effect on the whole system, I'm only going to keep to second order. The reason I have to go to second order is that, as we'll see, the first order contribution is 0. So the second order is the first non-vanishing term in the interaction. Okay? So this then is equal to minus 1 over h bar squared, integral t plus delta t dt prime t prime t traced over the environment. All right, so now we start having to make some approximations. So far, well, I've made one approximation. I've assumed that delta t is small enough that I can truncate this series and keep terms only up to second order in the interaction for delta t sufficiently small compared to the time scale of the dynamics. That was one of our assumptions. Now, the joint density operator at time t can be written as always as whatever there's some product contribution, which I'll say is whatever I get when I trace over the environment of the joint thing, tensored into tracing over the system of the joint thing, plus a piece that's the correlation. I can always do that. This is just whatever this is, subtracting off that piece. So now, and this is, I'll call the system, and this is the environment. Now we're going to make the Markov approximation. And the Markov approximation is to say that after the time scale delta t, which we chose to be large compared to the correlation time, that this is 0. Being compared to the correlation time. So again, the physical picture that you might think about, which I find useful, in why this is a reasonable approximation. Is again, think about my penny in the lake. I mean, what's happening here is, there's this temperature T bath here, and fresh copies of the bath are constantly entering. The first copy here gets correlated, carries off information, is correlated, but that correlation doesn't come back because all the colliding molecules now rethermalize, and that information never comes back. Now the next copy of the bath comes in, right? It's really the same bath because it's all at temperature T. Comes in, and new fresh molecules collide with my penny. They're at that same Boltzmann distribution. They collide and they go off, carrying off information. Each time this set of collisions happens, of course, the system changes. But the environment doesn't. The environment is different from the system because the environment has this huge number of degrees of freedom. The system doesn't. So really, I can say what is this, it's a good approximation, this is this. So what it's saying is that after each one of these coarse-grained timescales, a fresh copy of the environment is coming in. It's exactly the same, in the same state to this approximation. And whatever correlations that were created between the system and the environment, they're gone. They're rethermalized, and I just don't get them back. This is a key part of the approximation right here. We, of course, have the same picture if I go back to my atom at the vacuum. You know, here's the atom. All these, you know, I can break up the vacuum into all these little wave packets that are flying past the atom. There might be some tiny probability amplitude for this thing to decay into that wave packet. And then the next wave packet comes in. But this wave packet just flies off. It doesn't come back. And then a fresh copy of the vacuum comes in. And that's this approximation. So, this is the Markov approximation. And this is where the irreversibility happened, by throwing away those correlations. Right. Now, furthermore, we're going to take it to be the case, and we'll look at a specific case, where the interaction Hamiltonian, that the trace of the interaction Hamiltonian with the state of the environment is 0. We're just going to consider those situations. That's typically the case. That is to say, the interaction Hamiltonian has no mean field with respect to the environment. That's why, to first order, this is 0. And so, we get the following equation. The system state at time t plus vt, or delta t, the coarse-grained time, is equal to, or approximately equal to, what the state is at time t, and then what happens to the interaction, which now includes the second order. And that's the integral from t to t plus delta t, dt prime, the integral from t to t prime, dt double prime, the trace over the environment of the double commutator integral h interaction at t prime commuted with t Hamiltonian at time t double prime with the system at time t tensored into the environment, which is taken to always be in its equilibrium state. Yeah.
I know you just said it, but could you, why is this first term 0?
That's really an assumption that we'll see is typically the case, that the interaction, I could look at it this way. Typically, my interaction will be of the form a sum over operators, some system operators tensored into some back operators. That's a generic form. And we're taking it to be the case that the average of the bath operators in whatever the thermal state is 0. We're just considering those cases. For example, if this were the atom interacting with the vacuum, or even interacting with the black body radiation at thermal temperatures, this would be, the system operators would be some atom operators, and these would be things like A or A dagger.
That's true even if you have a laser field, right? I mean, oh no, never mind.
No, it's not, no, then the mean field is not 0. But if it's a state that has no coherence, then it's 0. Yeah?
And if that's not 0, I mean, the first order term then just contributes to your system only Hamiltonian,
That's
right?
right.
Okay.
Yeah, then it would just be, an effective shift.
Okay.
And you should just put that into,
Yeah. Okay.
This is just pick up on a comment that you, for a field with no coherence, this assumption would also be a good one.
will be 0. So if, for example, in this particular case, then if my density operator is diagonal in the number basis, so it has no coherence, then the expectation value of the bat is 0. That's the case we're going to look at. Well, next time. But let me just write one last equation here.
Just a technical question,
Yeah.
if I may. So the bound of the integral, the endpoints of the integral
Yeah.
They're
correct.
They're correct. Okay.
Yep. Because of the way I iterated, right? Because, well, I erased it now, but you have to do the nice
Okay.
series. That is correct. Yep. They are. If you can read them, they are correct. Okay, but I do want to write down one final equation. So now what I'm going to do is I'm going to subtract this from this. All this delta rho divided by delta t is then approximately equal to minus square delta t integral t plus delta t dt prime integral from t to t prime et double prime. And now I'm just going to expand out the double commutator and get the following. This is a messy calculation, and there's just no way around it. But you have to see it one time, at least. Because if you really want to understand open quantum system dynamics, you got to put through these details. All right, plus So that's just expanding it out, where all of these expectation values are the trace with respect to the environment's equilibrium density operator.
So the contents are still operators in the state basis.
Everything is an operator. Some of these operators are operators that act only on the system. That's this.
Well, if after you've done the expectation value on the environment of the,
This is also
Then that's a system
then
operator.
it's the system operator.
Correct. Right. These guys are all system operators. And in fact, you kind of see beginning to come into focus the Lindblad form, which had things that are multiplied by row on one side or the other and things that kind of sandwiched row. Kind of see it beginning to emerge from this. But clearly, if we're going to get to the Lindblad form, then something has to do with the correlation between what's happening in T and T prime. There've got to end up being delta functions here. And that's the final step. And it's basically the same thing that we did last semester when we did the Wigner-Weisskopf calculations. So I would encourage you to review lecture 14 from last semester, where we did the Wigner-Weisskopf approximation. So we're just going to use that stuff and go forward from there. All right? All right. Awesome.